This meeting is being recorded.
Okay, let me share the screen. Okay, screen is visible, class? Screen is visible?
Yes, sir.
Okay, so in our last lecture, we have discussed about the implementation of different Boolean equations using CMOS logic. Okay, and I hope you have through with this. Now, the next point of your unit number 3 is the properties of complementary CMOS gate. Okay, now what are different properties of this complementary CMOS gate? So high noise margin, this is the first one. No static power disconsumption, this is the second one. And what is third one? Comparable rise and fall time under appropriate scaling of PMOS and NMOS transistors. Okay, so these are the some of the features, or you can say properties of CMOS gate. High noise margin, no static power consumption, comparable rise and fall times under appropriate scaling of PMOS and NMOS transistors. So because of these properties, you can say it's a better device, right? So why no static power consumption? Because we have already discussed there are certain power dissipation factors, static and dynamic, that are involved, right? So in the any CMOS circuit. So why in case of this complementary CMOS, there is a no static power consumption? So the reason is very simple. In a steady state response, if you observe that VTC curve, okay, if you observe that steady state response, there is a no direct path between VDD and VSS, right? Why there is no direct path? Because CMOS is made up of PMOS and NMOS, and the output we are taking from the middle of the PMOS, where they have the junction, whether the pull up network and pull down network, it is connected. From that junction, we are taking the output. That means there is no direct connection between the VDD and VSS. Right. So that is the reason that there is no static power consumption. Right. Next point is a propagation delay analysis of this switch model. Okay. For example, if you consider this as an inverter, so there are two switches, right? This PMOS and NMOS. If you consider the two input NAND gate, so this A, B, PMOS is in parallel and this is in series. So already this point we have discussed. It is a two input NOR gate, whether this PMOS, A, B are in series and the NMOS in parallel. Okay, it's a load capacitance, you can say. So if you analyze this propagation delay model very carefully, what you find, right, after analysis of this propagation delay model, what you find, so if you assume CL is dominating, whatever the load capacitance that you have connected, it is dominating. So this Rn is equal to Rp, this resistance of the NMOS and PMOS, these are the identical, right? We have made that assumption. What assumption we have made? The Rn is equal to Rp, right? The Rn is equal to Rp. These are the resistance of minimum sized NMOS inverter. So in case of PMOS, Rp, and in case of NMOS, it is Rn, and these are the identical. Okay. Now, for the propagation delay from low to high, what is TPLH? What the TPLH indicates? This propagation delay from low to high. Okay. And now if you assume the worst case, right? If you assume the worst scenario of this, then the worst case, only one PMOS pull up the output node, right? The what would be the worst case? Out of these two parallel PMOS, only one PMOS can connect only to the output node. Now in that case, what you the TPLH, that is propagation delay from low to high, it is directly proportional to the RP, right? This is this register multiplied by the CL, that is the load capacitance, which is the dominating factor, right? Similarly, what is TPHL? Now we will assume now the wave or whatever the input wave is it's falling from its high level to low level. It's falling from its high level to low level. Now in that case, what will be the worst scenario? So both either of these two NMOS can one at least connected, right? So in that case, right, and these two are in series, these two are in series, so there is no question of one connected. But in case of parallel, if either A or either B is not in conduction, or only one PMOS it is conduction, that is sufficient to connect that part in case of parallel connection. But in case of series, what will be the worst case? So this TP high to low is directly proportional to the twice Rn into CL. Why the twice Rn? Because there are two NMOS and two resistors. CL is a one only at the output. So it is twice Rn multiplied by CL. Twice Rn multiplied by CL. Right? So this is the factor that you should consider while analyzing the propagation delay, or you can actually calculate the propagation delay for any of the circuit, right, using this analysis. Clear? Now the next point, the delay is important, right? So why the delay is important? So delay from 0 to 1, that means low to high transition to propagate to the output. Now how to find it mathematically in case of inverter? So TPLH is equal to CL multiplied by VDD, right? Why? How this equation we have because see, what is previous equation? It is RP, right? RP multiplied by CL. So by using the voltage divider rule, right? By using the voltage divider rule, you can easily calculate the RP value. It is as VDD divided by Kn in bracket VDD minus VTH. It's a square. Okay, after solving that equation, you will get a value of TPLH, that is propagation delay for a low to high. It is equal to CL multiplied by VDD divided by Kn multiplied by VDD minus VTN square. The same equation can be used for the TPHL. The same equation can be used for the TPHL. What is TPHL? That is a propagation delay from high to low. Propagation delay from high to low, right? Now in that case, how this equation will get modified? So it will be a CL, because CL is the output capacitance. It is not going to change. CL into VDD. VDD is also fixed one, because whatever the supply voltage you have applied, it is a fixed one. Instead of now Kn, it will be a Kp, that is constant for a PMOS, and VDD minus VTP, that is a threshold voltage for PMOS. What is VTN? Threshold voltage for NMOS, right? Only these many change will occur. Rest of the equation will be same. Rest of the equation will be same for TPHL, high to low, right? Now, how to calculate the value of Ron, right? For a particular CMOS inverter, right? What is Ron? It is a on register. It is a on register of that device. on register of that device. So now in case of CMOS, as you know, it is made up of PMOS and NMOS, right? In case of CMOS, it is made up of PMOS and NMOS, right? And this strongly depends on the operating region, right? Where you are finding this aron, it is strongly depend upon that operating region. So for a hand analysis, use the fixed value of R, which is the average of the two endpoints of the transition, right? So how to generalize this? So to generalize this, you can say, you can choose the value of R, which is the average of two endpoints of the transition. Clear? So for example, now we will find for this propagation delay of high to low, right? For an inverter, what is the Ron value? So Ron is equal to 1 by 2 R N MOS in bracket V out is equal to VDD plus R N MOS in bracket V out is equal to VDD by 2. Why this second is VDD by 2? Because it is connected to the ground, right? It is connected to the ground. So the total equation will become 1 half VDD upon ID. How this come? R and MOS. What is R is equal, V is equal to IR. So R is equal to V by R. So this you can replace this R and MOS is equal to VDS upon ID. V out is equal to VDD. Similarly, in the second case also for R and MOS, you can replace that R and MOS with ID VDS by ID. How this comes? Simple Ohm's law. V is equal to IR. So I is equal to V by I. R is equal to V by I. Right? So on that basis, VDS divided by ID and V out is equal to VDD by 2. By voltage divider rule, you can calculate this part. Now, next is a influence of fan in and fan out on delay. Okay. Now, before going to study the delay, you should understand what is fan in and you should understand what is fan out. Okay. Now, what is fan in? Right? What is fan in? The number of inputs that particular device can accommodate. In a very simple language, I am telling you. What is fan in? The number of inputs that particular device can accommodate. What do you think? If I have a NAND gate, right? If I have a NAND gate, so how many maximum inputs I can apply to that NAND gate? So that value, right? The maximum input that you can apply to that NAND gate, it is your fan in value. And it is specifically mentioned by that manufacturer, right? Whatever the NAND gate IC that you are using, so that manufacturer must have to mention its fan in and fan out value, because you cannot connect the infinite number of inputs to particular device. No, it is not allowed. There is a restriction, there is a rule. You have to study its fan in and fan out value, and then only you can decide how many inputs that you can apply or that device can accommodate. That is your fan in, right? Exactly opposite is the fan out. From that device, how many outputs you can withdraw or you can take out. Fan out means what? From that particular device, how many outputs that you could withdraw. It's a fan out, right? Now, so this fan in and fan out value also affects on the delay value. It also affects on a delay value. So for fan out, the number of gate connected to gate capacitance per fan out. This is the, in this way you can calculate the delay. And in case of fan in, that you have to consider the increase in resistance and increase in capacitance, right? So what will be the total equation? So for TP, propagation delay, A1 F1 plus A2 F2 square plus A3F out, that is the final output. So in this way you can add this term, right? Or you can summation the entire fan in and fan out value to calculate the influence of fan in and fan out on delay factor, right? See, fan in and fan out also contribute some sort of delay in any device. So you have to remember this point. Okay. Now next part is a ratioed logic. Okay. Now what do you mean by this ratioed logic? Okay. So what is goal to have this ratioed logic? So goal is to reduce the number of devices over complementary CMOS. The purpose behind this ratioed logic is to reduce the number of devices over a complementary CMOS. Okay, this is the purpose of this ratioed logic. Okay, and how to see this? So first, this is the resistive load, right? Then if you consider the second depletion load NMOS, third if you consider a pseudo NMOS, right? So by using any of the terminology, you can reduce a number of devices, right, over a complementary CMOS, right? If you can use a resistive load pattern, you can go for a depletion load NMOS, you can go for a pseudo NMOS, right? You can use any of the terminology to reduce a number of devices that you require over a complementary CMOS. And that reduced device or that reduced part is nothing but the ratioed logic, right? That reduced part is nothing but the ratioed logic, right? So this part, ratioed logic, we will continue in the next lecture. For today, we will stop here, and the remaining part we will continue in the next lecture. So remaining part we will continue in the next lecture. Thank you.